So in this class we will study about CRO. CRO is cathode ray oscilloscope. So cathode ray oscilloscope, we write cathode ray oscilloscope. It is also known as CRO. Okay. So cathode ray oscilloscope, it is an electronic instrument through which we can measure voltage, frequency, then phase difference. Okay. So this is a very important instrument in electronics. So we can measure the amplitude of this signal, peak to peak amplitude of any signal by using CRO. Similarly, we can measure the time period of the signal by using CRO. Okay. So if we are measuring the amplitude V peak to peak, then we can also determine VRMS. Okay. So in this way we can determine the voltage, unknown frequency, phase difference, time period, etc. by using CRO. So CRO, it basically consists of cathode ray tube. So cathode ray tube, it is the heart of CRO. Okay. So you can see this is the diagram of a cathode ray tube. It is also known as CRT, cathode ray tube. So cathode ray tube consists of electron gun, deflection system and the fluorescent screen. So this is the diagram of a cathode ray tube. This H stands for heater, K stands for cathode, then Z, this is Z. Z stands for control gate. A1 is pre-accelerating anode. What is A2? A2 is focusing anode. What is A3? A3 is accelerating or final anode. These are the deflection plates. This is vertical deflection plate, V1 and V2. These are the two vertical deflection plates and these are horizontal deflection plates. And this is the electron beam, that is spot on the fluorescent screen. So this is the diagram of a CRT. So first of all, by using this heater, by using this filament, cathode is heated, so electrons are produced. So electrons are produced because of heating of this cathode. K is cathode. So once cathode is heated, so after heating, electrons are emitted from the cathode. This is K. Then what is the function of control grid? Control grid, this is the control grid. Control grid is connected to negative potential with respect to cathode. Control grid, it is connected to negative potential with respect to cathode. So it can control the flow of electron. You can see that this is grid. If negative potential is given, this is generally connected to negative potential, and its negative potential, it is somewhat higher as compared to the cathode. So if the potential which is connected to the grid, it increases, then what will happen? Then the flow of electron, it will decrease. Okay. So it is used for, it is connected, this control grid, it is connected to this intensity. So intensity is dependent upon the control grid. Okay. Now this is A1 is pre-accelerating anode and A3 is final accelerating anode, whereas A2 is focusing anode. Okay. So you can see that this is A1 and A3, these are, and A2, voltage applied, you can write voltage applied is positive with respect to cathode. At A1, A2 and A3, the potential is positive and it is more as compared to cathode, and it is A3 is much more as compared to A2 and A1. Okay. Now these three, what is the function of grid? The function of grid is that it controls the intensity. It controls the intensity of the beam. Okay. So if we are applying more negative potential at the grid, then what will happen? Then a dull. This will be dim. This will be, you can see intensity. It will decrease. Now you can see A1, A2, A3. A1 is pre-accelerating anode. It will accelerate the flow of electron. A2 is focusing anode. A1, A2 and A3, these are connected to potential, positive potential. Okay, and A3 is final accelerating anode. So this by applying positive potential, it increases the speed of the electron. Now this is V1 and V2. These are the vertical plates, and H1 and H2, these are horizontal plates. Okay. So you can see, if we are applying, if V1 is connected positive, if this is connected to positive terminal of the battery, and if this is connected to negative, what will happen? So the electrons, you can see the electrons will move like this in this case. Okay. Now if it is reversed, then electron will move like this at this point. Okay. So this, by applying positive or negative potential at V1 and V2, it deviates the electron vertically. Similarly, H1 and H2, by applying some positive potential at H1 and H2, it deviates the electron horizontally like this. Okay. And what will happen if we are not connecting any potential to H1, H2 or V1, V2? Then it will directly, the electron will reach here. Okay. And this is fluorescent spin. Once the electron hits the fluorescent spin, then it will look brighter. Then this is aqueduct coating. What is the function of aqueduct coating? This is used. This is connected. Aqueduct coating, it is connected to this anode and this A3 anode. Okay, this is pre-accelerating anode and A3 is final accelerating anode. It is connected to these two anodes. So what is the function of this aqueduct coating? Once some electrons are reaching here, then it will be directly going to these anodes, and this will be used for the flow of electrons. Okay. So this is the function of aqueduct coating. Okay. And it is directly connected to A1 and A3. Okay. So this is all about CRT, that is cathode ray tube. CRT is the heart of a CRO. So we can see that the deflection plates in CRT, we are using two deflection plates. First is horizontal deflection plate, and second one is vertical deflection plates. So if some potential is applied to vertical deflection plate, it will move the electron vertically. Similarly, if some potential is applied to horizontal deflection plates, then it will move the electrons like left right, and here it is vertical and this is horizontal line, okay, horizontal movement of electron, and this is vertical movement of electron. This is due to the application of some potential to vertical deflection plates and horizontal deflection plates, and if no any voltage is applied to both the deflection plates, then the electron will hit at the center of the fluorescent screen. Okay, you can write the applications of CRO. First is analysis of waveform. Or study of waveform. Second, voltage measurement of waveform, any waveform. Frequency measurement of the waveform. Frequency measurement of the waveform. This is voltage measurement of the waveform. Then phase angle or phase difference of waveforms. Okay, so we can use CRO for analyzing or studying any waveform. Second, for the measurement of voltage, for the measurement of frequency, and for the measurement of phase difference. So one by one we can see. So we can see the applications of CRO. Okay. So first application is about study of waveform. Study of waveform. We can analyze the waveform by using CRO. Okay. So sinusoidal signals or other signals, it can be applied to Y input terminal. Any sinusoidal waves or any waves, it can be applied to the Y input terminal. Okay, and we can control the amplitude. We can control the amplitude or the time period. Okay, we can vary the signal by using vertical amplifier attenuator or by using time base. Time base control is one function, and second function is vertical amplifier attenuator. By using vertical amplifier attenuator, we can increase or decrease the shape of the signal that will appear on the screen of the CRO. Okay, and by using time based control, we can vary the horizontal position of the signal. Okay, so by using these functions, we can analyze the waves. Okay. Then second is about measurement of voltage. Suppose to the Y input terminal, we are applying some sinusoidal waves, okay, and to the X input some other signals are applied, okay. Then this is the display screen of CRO. And on the CRO display screen, if the wave, this is the shape of the wave. So if this type of wave is appearing on the display screen of a CRO, and if it is given vertical amplifier attenuator, it is 2 volt per centimeter, and time based control if it is given as 0.1 millisecond per centimeter, then how we can determine the Vrms of this signal and frequency of this signal, okay. So we can measure the voltage, we can measure the frequency of the signal by using CRO. How? So this is what? 2 volt per centimeter. This is sensitivity of CRO. Sensitivity of CRO. This is 2 volt per centimeter. This is 1 centimeter. This is complete 1 centimeter. Okay. Now we can measure V peak to peak. What is V peak to peak? So we have to count the number of boxes. This is 1, 2, 3, 4. This is from here to here. V peak to peak, it is 4 multiplied by this 2 volt per centimeter. 2 volt into 2, you can write 2. This is 4 centimeter. This is, you can write 4 centimeter into 2 volt per centimeter. So it is equal to 8 volt. So this is V peak to peak, it is 8 volt. So we have to determine what is V peak. So V peak of this signal, it is equal to V peak to peak divided by 2. Okay. So it is equal to 4 volt. Now how we can determine Vrms? Vrms, it is equal to V peak by under root 2. V peak by under root 2. So it is equal to 4 divided by under root 2 volt. This is Vrms of the signal, VAC, and this is V peak. So in this way we can determine the voltage. Then how we can determine the frequency of the signal? So in order to measure the frequency, first of all we have to find the time period. So this is 1, this is 2, this is 3, and this is 4. So how we can determine the time period? Time period of this signal is time period T. It is equal to this. We have to count 1. This is repeating. You can see this again. So this is one time period. Again this is repeating. So this is one time period. Time period, it is equal to 4 centimeter into this is 0.1 millisecond per centimeter. This is time based control. So if time based control is increased or decreased, then what will happen? You can see like this. it will vary horizontally. It will vary horizontally. If we increase or decrease the time based control, then it will like this. Time period it will be the same, but in figure it will vary horizontally. So it is equal to how much? It is equal to 4 into 0.1 millisecond. So it is equal to 0.4 millisecond. So we have to determine the frequency of this signal. So frequency it is equal to 1 by time period. So it is equal to. So in this way we can determine the frequency of the signal and VRMS of the signal. So voltage can be determined, frequency can be determined. Okay. Suppose the deflection sensitivity. Suppose the deflection sensitivity of CRO it is equal to 5 volt per centimeter, and to the Y input that is vertical deflection plate, if unknown AC voltage is applied, okay, and so Y input it is to vertical deflection plate, okay. Now if 10 centimeter long, if 10 centimeter long straight line, if 10 centimeter long straight line is observed on the screen, then how we can determine the AC voltage? You can see the deflection sensitivity of the CRO is 5 volt per centimeter. If any unknown AC voltage is applied to the Y input, then in that case how we can determine the AC voltage? Just like previous one, we have to calculate first V peak to peak. V peak to peak it is equal to how much? It is equal to this 10 centimeter long, 10 centimeter into the deflection sensitivity. This is 5 volt per centimeter. So it is equal to 50 volt. This is V peak to peak. Then we can calculate VP. VP is equal to 25 volt. Then how we can calculate VRMS? VRMS it is equal to V peak divided by under root 2. So in this way we can determine the AC voltage of unknown signal which is applied to the vertical deflection plate. Okay. So in this way we can determine the voltage, we can determine the time period, and by determining the time period we can determine the frequency also. Then we can see how to determine the unknown frequency. So unknown frequency can be measured by Lissajous pattern. So what is this Lissajous pattern? So Lissajous pattern it is displayed on the screen of CRO. How it is obtained? If we are applying signals to both X input and to both Y input, two different signals we are applying. If to the X input known frequency signal, signal of known frequency, you can write signal of known frequency, signal whose frequency is known, if it is applied to the x input, and signal of unknown frequency if it is applied to the y input. Okay, then Lissajous pattern is obtained. But how Lissajous pattern is obtained? If the difference in the two frequencies, if the difference between a known frequency and known frequency of the signal, it is some integer, if it is in integer, okay, integer or fraction of integer, then Lissajous pattern will be obtained. Lissajous pattern, it is stationary, it is still picture. So how we can calculate by using Lissajous pattern, how we can calculate the unknown frequency? So we can calculate the unknown frequency by using this formula, FB by FH. FB, it is unknown frequency, and FH is known frequency. Known frequency means the frequency of the signal which is applied at the x input, okay, to the, this is FH, to the horizontal deflection plate, and this is unknown frequency. So it is equal to number of horizontal tangencies divided by number of vertical tangencies. So if FB is unknown, if FH is equal to say 100 kilohertz, okay, and pattern is like this. So we can, how we can determine the unknown frequency? By using this formula, we can write FB by FH, it is equal to number of horizontal tangencies. Number of horizontal tangencies, it is 1, and here 2. You can see this is 1 and this is 2. Two lobes, two tangents. So this is 2 points. Suppose this is point A, point B, and this is point C. So it is equal to number of horizontal tangencies. It is C, it is 1, and number of vertical tangencies. Number of vertical tangencies, it is equal to 2. So unknown frequency, that is FP, it is equal to FH by 2. So it is equal to how much? It is equal to 50 kilohertz. So suppose another example I am taking. Suppose Lissajous pattern is like this, and known frequency of the signal that is applied to the x input, if it is equal to FH, if it is equal to say 50 kilohertz, then how we can determine FV? So by using the same formula, FV by FH, it is equal to number of horizontal tangencies. Number of horizontal tangency, it is equal to 1 divided by number of vertical tangency. Again it is equal to 1. You can see. So FV divided by FH is given 50 kilohertz, it is equal to 1 by 1. So FB it is equal to FH. So if Lessage's pattern is a circle, then in that case unknown frequency, it is always equal to the frequency of the signal that is applied to the X input. Means it is equal to FH. FH is known frequency. So in this way, by using Lessage's pattern or by using Lessage's figure, we can determine the unknown frequency by the use of CRO. Then how we can determine the phase difference? Now we can see that how phase difference can be measured by using CRO. So phase difference can be measured by applying two sine waves. Suppose we are applying two sine waves of the same frequency to X input to Y input, then we can see this type of Lessage's pattern will occur. Okay. Then how to determine the phase difference? By using this formula, we can determine the phase difference, that is sine theta, where theta is the phase difference between the two waves. It is equal to y1 by y2. What is y1? Y1 is the y-intercept of this Lessage's pattern. This is y1, this distance. What is y2? This is y2. Similarly, what is x1? X1 is this intercept x1, and x2 is the maximum distance. So sin theta, it is equal to y1 by y2, which is equal to x1 by x2. By using this formula, we can calculate theta. We can calculate the phase difference. If we are determining the theta, so we can determine the phase difference between the two signals that are applied to the X input and Y input of a CRO having same frequency. Okay, so in this way phase difference can also be calculated.